Hey everybody, my name is Anish, and today I'm going to tell you about our research on verifying hardware security modules. Hardware security modules, or HSMs, are powerful tools for building secure computer systems. The idea is that you can factor out core security operations from a host machine onto the separate device, the HSM, and this setup provides security under host machine compromise. So for example, consider the diagram on the right, and you two have security tokens like a YubiKey, where they're used to protect a private key used for authentication. And the idea is that even if the web browser or host machine is compromised, the private key is safe on this external device. There are many types of HSMs out there, and there are hundreds of millions of deployed devices in the wild. Unfortunately, like any computer system, HSMs suffer from bugs throughout the hardware and software stack. There are hardware bugs. Even embedded CPUs and systems on a chip do have hardware bugs. There are software bugs, like firmware bugs, buffer overflows, logic bugs, the usual suspects. And HSMs also suffer from timing side channels. The goal of our research was to figure out whether we can build HSMs without these security vulnerabilities. Is it possible to rule out hardware, software, and timing side channel vulnerabilities from HSM implementations? And we set out to do so under this challenging threat model, where we considered a powerful adversary that gains complete control of the host machine. So this means that the adversary has full control over the I/O interface to the HSM. Though we decided that physical attacks and other side channels were out of scope for our research. We're focused on remote compromise of the host machine, so we're looking at the kinds of things that a remote attacker can do, which is send arbitrary commands to the HSM over its I/O interface, but not do things like physically tamper with the HSM or look at RF side channels or things like that. Our approach was to use formal verification using a new verification framework we built called Knox. Knox supports high-level specifications that cover not only functional correctness, but also security and timing side channels. In our setting, verification spans both hardware and software, so we're able to capture bugs in both and also in the complex interactions between hardware and software. And Knox uses symbolic execution, so it's highly automated and has low proof overhead of less than one line of proof per line of code in the implementation. Knox is the first framework to verify correctness and security of hardware and software, including timing side channels. Prior work on hardware-software co-verification is focused on correctness, not security, and application security verification doesn't cover hardware or timing side channels. Our work introduces a new security definition called information-preserving refinement. And through this definition, we formalize the intuition that an HSM doesn't leak any information, including through its timing behavior. To verify HSMs using IPR, we built the Knox framework. And then as case studies, we built and verified 3 simple HSMs. And we showed that our approach rules out hardware bugs, software bugs, and timing side channels in their implementations. This talk focuses on the definition of IPR as well as the case studies. As a running example, we consider this pin-protected backup HSM, which is inspired by the pin lock on phones. What's shown here is a simplified version of one of the case studies in our paper. The main functionality of this HSM is to protect a secret with a pin and limit the number of pin guesses when retrieving the secret. So on the left is the functional specification, and we can see that it exposes 2 operations, store and retrieve. Store stores a secret in a pin, and retrieve allows for retrieving the secret given a pin guess, and it enforces a guess limit. The spec is just describing input-output behavior at the function level, and there's no notion of timing here. We couldn't imagine anything simpler for describing the intended functionality of this HSM. This makes for a really clean specification. Implementations, on the other hand, are much more complex. On the right, we see a schematic for an implementation, and the implementation includes hardware and software. So this includes the CPU, the code that runs on top of the CPU, and other stuff inside the system on a chip, like the peripherals and persistent memory and so on. This is the HSM, and the interface that the HSM implementation has to the external world is a bunch of wires. From the host machine's perspective, the host is connected to this HSM, and the host can read the logic levels on the output wires, set the logic levels on the input wires, and it can also wait for the HSM to execute. We really are talking about signals on wires here. We're modeling the implementation at a really low level. And so the big question here is, how do we relate the implementation to the specification? We want to capture not only functional correctness, but also security, this non-leakage property, that the wire level behavior of the implementation should leak no more information than the specification does, including through its timing behavior. Recall that in spec land, we have no notion of timing, only input-output behavior at the function level, and we want to make sure that the implementation is free of vulnerabilities. Like it shouldn't, for example, implement a pin comparison with a non-constant time comparison operation, because that would leak the number of bytes that match between a guess and the saved pin. The tricky part in relating these two is that the implementation and spec look nothing like each other. The implementation is at the level of wires, but our specification is at the level of functions. There's just no notion of wires there. And so to connect these two, we introduced this new security definition that's called information preserving refinement, or IPR. And it's defined as an indistinguishability between a real world and an ideal world. This definition is inspired by the formalization of zero knowledge in cryptography. In the real world, we have the implementation, and the real world is set up to, well, model the real world. And in the ideal world, we have a specification. And the plan is to set up the ideal world so it's correct and secure by construction, and then say that these two are indistinguishable from each other, that an adversary shouldn't be able to tell the difference between the real and ideal worlds. The problem here is that these interfaces are incomparable with each other. We can't say that they're indistinguishable because, well, they're not. And so what IPR does is introduces two new components that act as interface adapters in each direction. So on the left side, we have the driver, which exposes a functional interface, and it's implemented in terms of wire level I/O with the implementation. And on the right side, we have the emulator, which exposes a physical interface, matching the interface of the implementation, and the emulator is implemented in terms of querying the specification. The driver and emulator are not part of the implementation in the sense that these are not things that we build and run in practice. They're constructs that exist for the formalization of the security definition and the proof. So now let's take a closer look at each one of these. Now that we've introduced the driver and the emulator to make these interfaces match up and we can compare these worlds, let's see the role that the driver and emulator play in the security definition. The driver translates spec level operations to wire level I/O. This one's pretty intuitive. It's like a device driver in an operating system, and it describes how a host machine must behave in order to invoke spec level operations on the HSM. So it's trusted, it's part of the specification. On the right side, we see a code snippet. This is part of the driver for our example HSM, and this is showing how the store operation, highlighted in blue, so this is the spec level operation, eventually boils down to wire level I/O with the HSM, and those operations are highlighted in red. And this driver is describing how it does I/O over UART. So it's following a UART protocol because that's what this particular implementation expects. The driver helps us capture functional correctness. When interacting with the implementation following the driver, it should behave like the specification. Now let's look at the emulator. This one's a little bit less intuitive, but it's really interesting. What the emulator is supposed to do is it mimics wire level behavior. It aims to perfectly match at a cycle accurate level the behavior of the implementation. But the emulator has to do so without direct access to the secrets that are in the real circuit. But what the emulator does have access to is the spec. It can make queries to these spec level functions. And the idea is that if the real circuit has some timing behavior that you can look at, the emulator should be able to perfectly reproduce that timing behavior given only access to the spec. And this captures the idea that the circuit implementation leaks no more information than is available through the specification. The emulator is a proof artifact. As part of our proofs, we have to construct an emulator. One just needs to exist, and its existence captures non-leakage. So if one exists, the circuit doesn't leak more information than the spec. Now you might ask, what happens if we have a buggy or insecure implementation? Well, in that case, an emulator just doesn't exist. If we have an implementation that, for example, leaked information about the pin through timing, doing this non-constant time comparison operation, then given some input, the output might be available at different times depending on how many bytes of the pin guess matched. And if that's the case, this behavior is not emulatable. If we try to construct an emulator, well, we could get the output value in some sense, like we could tell that the pin guess is incorrect by querying the specification, but the spec has no notion of timing, and it doesn't tell the emulator how many bytes match, so it's not possible for the emulator to reproduce this timing difference that the real circuit exhibits. And this is how IPR rules out timing side channels and implementations. And in cases where the implementation doesn't leak, if we have a secure implementation, then an emulator exists. We can construct an emulator. And just to give you a sense of what that strategy looks like, how we prove, or how we construct emulators as part of the proof, at a high level, what we do is we actually take the implementation and construct a dummy version of it, like copy paste the circuit. It doesn't have the secrets in it anymore, but it more or less behaves like the real implementation. And the only place where we run into trouble is when the real circuit is operating on its secret state, while our dummy circuit doesn't have secret state, so it's going to be computing on some garbage information. And so what the emulator does is it uses this dummy circuit and adds a little bit of stuff around it to replace the operations it does on the secret state with queries to the specification. So this is the general strategy we use for constructing emulators. Taking a step back, what does this IPR definition say about HSMs? Well, it transfers security properties from the spec to the implementation. So among other things, given the spec, what can we tell about the implementation at the wire level? Well, it only reveals secrets when the correct pin is supplied, it enforces guess limits, it forgets the old secret and pin when store is called, and it doesn't leak past pin guesses, among other things. And all of these properties hold on the implementation at the wire level, no matter what crazy things the host machine does, even if it's compromised, even if it's disobeying the I/O protocol and trying to subvert the HSM. Basically, IPR lets us prove that the implementation is just as good as the spec. To verify HSMs using IPR, we built the Knox framework. And this framework uses symbolic execution. It's actually symbolically executing the entire circuit and the code that's running on top of it. You can think of it as we're inlining the code into the circuit and then symbolically executing the whole thing. And to make the scale to reasonably sized HSMs, we rely on the developer to provide untrusted guidance. It's basically extra proof input to the system. And then to evaluate the new definition of IPR and the Knox framework, we did some case studies. We built and verified 3 simple HSMs, and these are real HSMs that run on an FPGA. On the hardware side, even though they're simple, they exhibit many of the complexities present in real HSMs. So there's a minimal RISC-V CPU in all of our case studies. A couple of the examples have hardware cryptographic accelerators, their I/O peripherals like UART, and a couple other components in the system on a chip. This is all implemented in about 3,000 lines of Verilog code, and actually most of it is off-the-shelf code. On the software side, we have in a combination of C and assembly, control logic, peripheral drivers, and in a couple of our examples, crypto-related code as well. So we have an implementation of HOTP and HMAC. And this is some interesting interaction between software and hardware. So we have part of the implementation in software, and then for the actual SHA-1 block function, that's done in hardware, so it's fast. We have really succinct specifications for these HSMs, and low proof overhead, less than 1 line of proof per line of code. But really, the core of our evaluation was showing that this approach catches bugs in the implementation. And I can't go through all of them, all the bugs we found right now, so see the paper for those. But I'm going to go through one really interesting one. And this example touches on hardware, software, persistence, and timing. It's this really subtle bug. All right, so the code you see on the right is a code snippet from this running example, this pin-protected backup HSM. It's from the retrieve operation. And what this code does is it first checks to see if the pin guess limit's exceeded, and then after that, it does a comparison, a constant time comparison of the guess with the saved pin. Also now, let's look at the left side. This is a timing diagram, time going down vertically, and this is what actually happens when this code is compiled and run on our particular circuit. It turns out that when we do this comparison operation, if the guess is correct, after some short amount of time, we set this bad guess count to 0. This is in persistent memory, so we're persisting this bad guess count equals 0. But in the case that the guess is incorrect, it takes a longer amount of time to persist the incremented bad guess count. All right, this is just what the hardware happens to do given the way the software is compiled. Now, unfortunately, this can be exploited. It turns out that if an adversary guesses a pin, waits for just the right amount of time, and then resets the device, something interesting happens. If the pin guess was correct, then the bad guess count has been reset to 0. And if the adversary's guess was incorrect, well, we haven't yet gotten to the point where we persisted the updated count. And there's no outputs during this whole sequence. The output happens much later, and we've already reset the device before then. But this is still a security issue, because what the adversary can do is, even though they can't tell from the outputs which branch they took, they can just guess all the pins from 0000 through 9999, and by doing that and resetting, doing that and resetting, this whole process overall will reset the guess count to 0. So this allows for bypassing this guess limit. And this can be used as a gadget to construct a full attack where you can extract the secret without knowing the pin, so bypassing the guess limit. And what's nice is that IPR rules out this sort of bug. This implementation leaks more information than the spec. The spec enforces the guess limit, and this implementation, well, doesn't. And so yeah, verifying IPR helped us catch this bug. And what's kind of interesting is that this is a real issue that implementations struggle with. So we looked at some real-world HSMs and found a similar code pattern in the solo keys code. It's doing a similar branch based on whether the pin guess is correct or not, and then decrement versus reset the guess count. And some other HSMs that are out there have really carefully written code to avoid this sort of an issue. This particular bug also highlights the importance of hardware-software co-verification. It has to do with the interaction between hardware and software and persistence and timing. So we wouldn't have been able to catch this sort of a bug by looking at only software, for example. And this demonstrates the power of the Knox approach. So in summary, we presented the definition of information-preserving refinement, which captures the idea that an implementation reveals no more information than its specification allows. We built the Knox framework and then did some case studies where we built and verified HSMs. For more information on Knox, see the link at the bottom of the screen. And we also have code there for both the framework, our 3 example HSMs, and a bunch of simpler examples that I strongly encourage you to take a look at if you want to see what emulators and drivers and specs look like for our HSMs. So that's Knox, and I'm happy to take any questions.